This video is about vector spaces, and we're going to do four things. We're going to define a vector space, introduce some common vector spaces, we'll prove a few theorems about vector spaces, and then we'll do a bunch of examples to determine if given sets and definitions form a vector space. And once we go through the first three here, this should make more sense what this even means. This video may be a little bit longer than average, particularly this first section where we define a vector space, because this is the first time in this class and maybe in your math career up till now that we've seen axiomatic and abstract math. So the definition of a vector space, and really all the rest of the stuff that comes after as well, is both axiomatic and abstract, and I'll explain those things as we go along. To illustrate the idea of axiomatic math or an axiomatic system, let's consider a game that may be familiar to some of you. If we look at this thing, and if I said, what is this? Most people would say this is a chessboard and it's got chess pieces on it. But that's just because that's what we're used to thinking of it as. This 8 by 8 square checkered board is the same board that's used to play other games, though. If we didn't make any distinction between these chess pieces and just considered them all white discs, for example, and the same thing with the black pieces, we could play checkers. We could play the game of checkers with these pieces on this board. And if we really wanted to, we could make up even different games. When my kids were little, they used to play with the chess pieces on the chessboard like these were army men, and they would just play war games and just make up their own rules. The point here is that these objects themselves are neutral. They have no meaning until we assign the meaning. And that's kind of what an axiomatic system or axiomatic math is like. There are these things called axioms, which are like the rules of the game. What's interesting about the game of chess, and why probably so many people like it, is that there are lots and lots of variations on what can happen. Millions and millions of different games that could be played. If white moves this pawn here first, and then say black moves this knight here on the second move, and then white moves another pawn, and then black moves another pawn, or etc., etc. And there's a sequence of moves that describe a game. And we could talk about what are all the possible games that can be played, what kinds of combinations of moves can lead to desirable outcomes, like, say, checkmate or defending against checkmate. In a similar way, axiomatic math systems are sets of objects, like in this case, a chessboard with pieces on it. In our case, we're going to talk about, instead of chess pieces, we'll talk about vectors, and then rules or axioms about the nature of those objects. So what is a vector? What are the rules of vectors? Just like we say, what is a rook? And what are the rules about how rooks can move? And then we study all the possible results of those objects and those rules. And math is interesting like chess, but also very useful. So if we define our objects and our axioms in useful ways, the resulting axiomatic systems can describe the world that we live in and the nature of the universe, physics in general, and be very useful for predicting what's going to happen. Okay, with that little intro, let's look at the definition of a vector space. This is one definition. It's quite long, so we're going to take our time to go through this. If we are given four things, two sets and two definitions, if those four things satisfy 10 rules, which we'll call axioms, then those four things form a vector space. Okay, so that's the big picture. So what are these four things? Well, we have two sets and two definitions. In particular, we have a set of objects that we call vectors and a set of objects that we call scalars. Now, the vectors are not defined yet. And in fact, the axioms that follow will define what a vector is, and we'll see lots of examples of what vectors could possibly be. The scalars are objects in what's called a field. And a field is a thing that is already defined in math. It's part of that abstract nature that I mentioned earlier. In abstract math, we study things like fields, and you can think of a field as just a set of numbers. In linear algebra, we call them scalars to distinguish them from vectors, but you can just think of the field as the set F. It's going to be a set of numbers. In this class, unless we specify otherwise, the field F will be the set of complex numbers. Then for every vector u and v in the set V, we define how to add two vectors together. We also define how to multiply a vector times a scalar. So if alpha is a scalar or a number in the field F, then we define a number times a vector. So with those two sets and those two definitions, we then look to see if those four objects, the two sets and the two definitions, satisfy all 10 of these equations or rules, which we call axioms. And if they do, then we have a vector space. And if any one of these is not satisfied, then what we have is not a vector space. I won't take the time right now to go through each of these in detail. Make sure you read about them in the book and study them here in these notes. For now, I'll just point out some of the most important ones. The first two are especially important. The first one is called AC, which stands for Additive Closure. And it may look a little strange. It says u plus v is in v. Remember this funny looking symbol that's like a curvy capital E is the Greek letter epsilon, and it means is in. We put parentheses around the u plus v to emphasize that this is a single vector. So in our definition of vector addition, when we add two vectors together, we get another vector. And we put the parentheses around u plus v to indicate that these three symbols really mean one vector, and that one vector is in v. So the way to think of this is if you add two vectors together, you get a vector in v. You don't get a vector that's outside of v. You don't get something that's not a vector. So the idea of closure, we say v is closed under vector addition. Closure means if I were to take two vectors in v and add them together, I can't get anything outside of v. We could draw a little picture like this of additive closure. If this is the set v, here's the vector u, here's the vector v, here is the sum of u and v, and it's inside the set v. It can't be, in particular, out here, outside of the set v. Otherwise, v would not be closed under vector addition. Scalar closure says a similar thing, which is that if I multiply a vector u that's in v by a scalar, remember this scalar alpha is not in v, it's in f. If I multiply a vector times a scalar, I will get another vector, and that vector has to be in v. So we say v is closed under scalar multiplication. So here's a little picture of scalar closure. I've got the vector v, alpha comes from the field, and if I multiply alpha times v, I get a vector that's inside the set v. I do not get a vector that's outside the set v. Every scalar multiple, which is what this is called, of vectors inside v are also inside v. So we say v is closed under scalar multiplication. Another really important axiom is number 5 here, the zero axiom. This funny symbol, this backwards capital E looking thing, means there exists. So the zero axiom says there exists 0 in v such that u plus 0 equals u for all u in v. And this upside down capital A looking thing is a symbol that means for all. Now we have to be careful not to assume that we know what the zero vector is. This is generally not the number 0. When we talk about different kinds of vectors, we have to figure out what the zero vector is based on this equation. This equation is actually a definition of 0, and we'll see how this works when we get to some examples. Finally, it's important to understand that equality of vectors is referred to, for example, when we write things like u plus v equals v plus u in the commutativity axiom, but we do not explicitly refer to what equality means. when we are defining the vector space. So in practice, when we give specific vector spaces, like we're going to do in just a minute here, we need to explain, well, what does it mean for vectors to be equal? Okay, so let's consider our first and most common example. This is Cn. This is the column vector space that we've studied previously. So in this vector space, the set V is a set of these column vectors that we've studied before. The field is C. The definition of equality we saw previously, but let's write it out again real quick for review. So remember, two vectors u and v, two column vectors here, are equal if the component in position I of vector u is equal to the component in position I of vector v for I equals 1, 2, 3, up to n. So for all I from 1 to n. The definition of addition is the same as we saw before. The component in position I of the sum of u and v is just the sum of the components in position I. The definition of multiplication is given by this equation, the component in position I of alpha times u, this new vector alpha u, is equal to alpha times the component in position I of vector u. This notation may still be a little unusual if you are not used to it yet, but it's very efficient, which is why we use it. We can do a quick little example to illustrate these definitions. If vector u is in C2 and its components are 1, -1, v is 3, 2, u plus v is the vector 4, 1, where I simply add the components of u and v together. Similarly, -3 times u is equal to the vector -3, 3, so I just multiply each component in u by -3 to get -3, 3. Just because we call this a vector space, or because we called it a vector space before, doesn't mean that it satisfies all 10 axioms. Remember, these two sets and these two definitions have to satisfy the 10 vector space axioms in order for Cn to really be a vector space. And the way we would determine that is we would check each of the 10 axioms and see if they're satisfied. I'm only going to check one of them, the additive closure axiom here, to see if u plus v is in Cn based on this definition. And then I recommend that you check the other 9 on your own. If we take two arbitrary vectors in Cn, u and v, they would look like this. Here's u and here's v. If we add them together using the definition, we just add each of the components together and we get a third vector. And this vector is in Cn, or v in this case. Why? Well, because if u1 is a complex number and v1 is a complex number, if we add them together, we get another complex number. So we are relying on the additive closure property of the field of complex numbers. You may not have thought of this before, but if you add any two complex numbers together, you'll get another complex number. Of course, what else would you get? But it's possible to take a set of objects or a set of numbers and add them together and get a number that's not in the set. But for the complex numbers, the set of complex numbers, they are closed under addition, and that means that Cn, the vector space Cn, is closed under vector addition because we've defined vector addition in terms of addition of complex numbers. So axiom AC is satisfied. Another important vector space that we haven't seen yet, but we will see a lot going forward, we write with a capital M and a subscript mn, and this is the vector space of m by n matrices. So we read this as mmn. V is a set of matrices A, or the set of A such that A is an m by n matrix, where m and n are integers, and F is the complex numbers as usual. We define the sum of two matrices using this notation that we saw before. This means the number in row I, column J of the sum matrix A plus B. So this new matrix, the sum of A and B, the number in row I, column J is the sum of the number in row I, column J of the matrix A and the number in row I and column J of the matrix B. Likewise, the product of a scalar alpha times the matrix A, the number in row I, position J of that new matrix, is equal to the scalar alpha times the number in row I and position J of the matrix A. These, again, may look a little strange, just like the column vector notation, but when we see the examples, it's equally trivial, so I'm not going to take the time now to do a little side example here. You can look at those in the book. This vector space can be a little bit tricky because matrices have vectors inside of them, or we can imagine that the entries inside the matrix form rows and columns, and we can talk about the columns as vectors and the rows as vectors, especially the columns. And we need to understand that the column vectors inside a matrix are not vectors in MMN. So we can do a little example to illustrate this. So here's a very boring matrix A, which is in the vector space M23. It's a 2-row by 3-column matrix, so it's in the vector space of 2 by 3 matrices. This matrix is a vector in this vector space. Inside the matrix, it's got columns. So if I call A1 the vector 1, 4, that's the first column of A. The second column of A is the vector 2, 5. The third column of A is the vector 3, 6. A1, A2, and A3 are in C2, the vector space of two-dimensional column vectors. They are not in M23. The common mistake students make is to refer to the column vectors of a matrix as vectors in the vector space of matrices. So watch out for that. A special vector space is the zero vector space. This is kind of a strange one. The set V contains a single vector, just the zero vector, and F is the set C of complex numbers. To get the zero vector space, you start with any vector space that you already know about and put the zero vector into a set all by itself. So for example, if we took the vector space C3 of three-dimensional column vectors, here's just a few vectors in C3. There's infinitely many, but I've drawn 4 of them here. And here's the zero vector. And if I make a new set, call it V, and the only thing in there is going to be the zero vector, if I keep the field C of complex numbers, I keep the definition of addition and multiplication for C3, and use that with V. C is my field, keep the same definition of multiplication and addition, then I get what's called the zero vector space. Okay, let's convince ourselves that this is actually a vector space. It has to satisfy all 10 of the vector space axioms. We can start with additive closure. If I add any two vectors in the vector space together, I should get another vector in the vector space. Well, there's only one vector in there. So if I add it to itself, I have to get the only vector in there. So 0 plus 0 has to equal 0. Now that may seem obviously true, but remember, we can't assume anything about vectors. We have to use the definition of addition to figure out what the sum of any two vectors are. Well, we also know that axiom Z says u plus 0 equals u for all u in V. In other words, if this is indeed a vector space, we know that this axiom has to hold. So what we can do is take the zero axiom, substitute in a 0 for u, because 0 is the only vector in there, put in 0 for u here and here, I get this equation, 0 plus 0 equals 0. So if the zero axiom is true, then the additive closure axiom is true. Well, we know that the zero axiom is true because it's got to be true in C3. So the zero vector in C3 satisfies axiom Z for all vectors in C3, including itself, including the zero vector. So we know that it is satisfied in our new zero vector space, and therefore the axiom AC is also satisfied, and the zero vector space is closed under vector addition. Scalar closure would have to say this: alpha times 0 has to be equal to another vector in the vector space, but since 0 is the only vector in there, alpha times 0 has to be equal to 0 for any scalar alpha that we want. To show that this is true is a little bit more involved than showing additive closure, so I wrote a little theorem here and a proof. And this is our first theorem and proof about vector spaces, so we'll go through this in a little bit more detail than usual. These proofs about vector spaces using the vector space axioms are both very simple and straightforward, and they can sometimes be kind of tricky and not obvious. So let's walk through this here. The theorem says that given a vector space V over F, alpha times 0, the 0 vector, because it's a bolded font, we know we're talking about a vector here. Alpha times 0 is equal to the 0 vector for all alpha, for all scalars in the field F. By the way, as an aside, notice that this just says given a vector space V. It doesn't have to be the 0 vector space. So this theorem is actually true in every vector space. Okay, on the face of it, what we want to show is pretty simple. A scalar times the 0 vector equals the 0 vector. And it might seem intuitively obvious based on our experience with numbers. If we were talking about the number 0, sure, if you multiply any number times 0, you get 0. But we can't use our knowledge of numbers to assume that vectors behave the same way. We have to prove that they do based on the axioms, based on the rules. So going back to our analogy about a chess game, you might be familiar with checkers, which is played on the same board and maybe with black and white pieces if you're used to that, but you can't use the rules for checkers to play chess. Okay, so the first step here is using the zero axiom. And actually every single step along the way is justified by an axiom. Part of the nature of an axiomatic system is if you want to do a proof, you have to use only the axioms. Every single step that you make has to be justified by an axiom. Now later, as we build up more theorems, we can use theorems to prove other theorems. It's sort of like, building a building. You lay the foundation. Well, the foundation is the axioms. And then you start building on top of the foundation one theorem at a time. And once you get some theorems on your foundation, then you can build more theorems on top of your theorems. But for now, we only have the axioms. And so every single step here has to be justified by an axiom, which is part of the reason that this looks kind of strange. And it may seem not at all obvious why we do what we do here. So in the beginning, I encourage you not to worry about the question why. Focus on how. See, how does this work? And just think of it as an interesting puzzle that indeed you can convince yourself if you go down step by step, yeah, I guess this is equal to this is equal to this, and you can get down from here to here. And what do you know? Alpha times 0 equals 0. So we've proven the theorem. Okay, so alpha times 0 is equal to alpha times 0 plus 0. That's just the 0 axiom. It says any vector, like alpha 0, plus the 0 vector is just equal to the original vector, alpha 0. Now again, why did we start with this? Well, the reason we started with this is because that will lead to this and this and this and this and get us down here. But it's not obvious. Until you have experience doing this, you wouldn't know to do this. So just relax, don't worry about it. Just watch what happens. Okay, so now what I'm going to do is replace 0 with alpha 0 plus the opposite of alpha 0. This is called the additive inverse axiom. Now, this is one of the ones I skipped before, so you can go back and look at that in the list. So we're replacing 0 with alpha 0 plus the opposite of alpha 0. Then I'm just going to move these parentheses. This is an associative property, so instead of grouping these two together, I'm going to group these two together. So that's all I did here. That's the associative, additive associative axiom. And then I'm going to factor out the alpha. And so these are properties that are the same as for real numbers. This is the distributive property of vector addition. So I factor out the alpha here. Now remember, the reason I can do this is because of this axiom, not because factoring is a thing. It's a thing for real numbers, and you learned that in an algebra class. But you can only go from here to here because of this axiom. Okay, and then 0 plus 0 is 0. That's the 0 axiom. So I have alpha 0 plus the opposite of alpha 0, and that just adds up to 0, again by the additive inverse axiom. Now I went through that kind of fast, so if you didn't catch it all, that's okay. Go back and rewind this part if you need to, or just read more examples of these in the book and in the notes. Okay, so if we kind of zoom back out and think about for a minute what just happened, well, we proved that alpha times 0 is equal to 0. And so in particular, that means the 0 vector space is closed under scalar multiplication. Because remember, we wanted to see if a scalar times a vector in V gave us another vector or the only vector in V. All right, I'm not going to prove the rest of the axioms. You can check those on your own. Okay, I'm going to pick up the pace a little bit now, just for the sake of time. So I'm not going to go through the proof of this theorem. I'll just point out this is a really useful theorem. The additive inverse of any vector in a vector space is unique. So this additive inverse axiom tells us that an additive inverse exists, but it doesn't tell us that it's unique. So this is a proof that tells us that the additive inverse is unique. Uniqueness proofs are a common and important kind of proof, so I will say something very briefly about how to prove that something is unique, since this is the first time I think that we've done this. And there are two pretty straightforward steps. First, you assume that two things satisfy the definition of the thing. Now, this is kind of lazy here with my language. It's like Dr. Seuss, thing one and thing two. In this case, my things are vectors, and in particular, the additive inverse of a vector. So if I want to show that the additive inverse is unique, I'm going to assume that there are two additive inverses. In particular, two things that satisfy the definition of the additive inverse, which means that those two vectors rather satisfy the additive inverse axiom. And then show that those two things are identical. So if we come back to our theorem, I start with this equation, and again, I'm not going to go into the why of that. And then I assume that there are two vectors, v and w, here, that are both additive inverses of the vector u. So that means u plus v is equal to 0, and u plus w is also equal to 0. That's just the additive inverse axiom. And then we use some more axioms to show that v is equal to w. So it's the same as w. So really, there's only one additive inverse. Our last common vector space example is Pn. And Pn is similar to Cn, but instead of column vectors, we have polynomials. So in this example, v is the set of polynomials of degree less than or equal to n with complex coefficients. So in set notation, we can write v like this: p of x, and this is a function, a polynomial function, say from calculus, alpha 0 plus alpha 1x plus alpha 2x squared plus alpha 3x cubed, etc., up to alpha n x to the n, where the alphas are complex numbers. The field is C. The definition of addition is here, multiplication is here. These are the definitions from calculus. We don't use these very often in calculus or pay a lot of attention to them, so they may seem unfamiliar. But remember, this is a new polynomial. It's a single polynomial, that's why I have the parentheses here, p plus q of x. And p plus q of x, the sum polynomial, is equal to p of x plus q of x. And strictly speaking, remember that this is the image of that polynomial. So x is your input, and this is the output. Okay? So x is an input here, p of x is the output, x is an input here, q of x is the output. So the output of this sum polynomial is the sum of the outputs of these two. We can illustrate this with a quick little diagram over here to the side. Here I've got the polynomials p, q, and p plus q. Notice these are all just single polynomials. This is one polynomial. It's a single box here. It's just labeled p plus q. It's the sum polynomial, the sum of these two. They all have inputs x. The output of polynomial p is p of x. The output of q is q of x. The output of p plus q is p plus q of x. And the parentheses here just group this together as a single polynomial. And it's defined to be, this sum is defined to be simply this number plus this number. Similarly, multiplication is defined like this. The product alpha p of x is alpha times p of x. We can diagram that one down here. Here's my new polynomial alpha times p. The input is x, the output is alpha p of x, which is defined to be simply this number back up here, p of x, multiplied by alpha. You can check the vector space axioms on their own for this one. I'll skip that for the sake of time. Now we come to the last objective in this video. We're on the home stretch, so hang in there. We're going to do some examples that are similar to the homework exercises and the quizzes and exams. So this hopefully will be worth your while. In the first example, we're given this set V. So this is a two-dimensional column vector, so this might be in C2, except that it's not C2 because as we'll see in a minute, the definitions are going to be different. So we've got a column vector with two complex numbers in a column like this, but here's our definition of addition. If I take the vector xy and add the vector wz, we get 0, 0, so we get the 0 vector. So this is weird. These are just arbitrary vectors, in this vector space, and you add any two arbitrary vectors together and you always get the zero vector. It's kind of a strange definition. Add any two vectors and you always get zero no matter what the two vectors are. But we can make up anything we want. The only question is, well, then is this going to be a vector space? The definition of multiplication is the same as for C2. So alpha times a vector is just a vector whose components are alpha times the components of the original vector. And we want to know, is V a vector space over C? And this language, remember, means that C is our field. So F is C in this case. Well, we need to check the axioms. And for every problem like this, where you're given a set of vectors, you're given a set of scalars, you're given a definition of addition and multiplication, and asked, is this a vector space? Well, as they say, there's no royal road to learning. You just have to check all 10 axioms. If you get lucky and the answer is no, you might figure out one of the axioms that's not satisfied kind of quickly. And the more you do these kinds of problems, the more you'll develop an intuition about which axioms may not be satisfied. But otherwise, you just start at the top and go down 1, 2, 3, 4, 5, etc. until either you find an axiom that's not satisfied or you get to the end and you find that they are all satisfied. In this particular case, lots of axioms are satisfied, like commutativity. xy plus wz is equal to wz plus xy. If I just change the order here, they're equal. Why? Because this is 0 and this is 0. The sum of every pair of vectors is 0. If you get down to the zero axiom, though, you'll see that it's not satisfied. The zero axiom says xy plus the 0 vector has to equal xy, the original vector. But because of our definition of vector addition, we know xy plus the 0 vector is 0, because the sum of any two vectors is 0. And as soon as we find a single axiom that is not satisfied, we can stop and we can say V is not a vector space over that field, C. In this next example, the set V is the set of polynomials P of x equal to ax squared plus 1, where a is a complex number. So if we look at this for a minute here, this is not all second-degree polynomials, only the ones that are in the form of a number times x squared plus 1. So that part's pretty specific. Notice there's no x term. There's no ax squared plus bx, for example. So you can't have any x terms. You've got to have an x squared term. Although if a is 0, I suppose we could have, 0x squared, so we don't have to have an x squared term, but we can have an x squared term. We can't have an x term, because that's not in here. And then the constant term has to be 1 for all these polynomials. To illustrate V a little bit, we can think about some polynomials that are in V, some examples of polynomials in V. So 3x squared plus 1, it's a number times x squared plus 1. Minus pi x squared plus 1. 0x squared plus 1, which we could write as just the number 1. So 1 is actually in V because it can be written as a number times x squared plus 1. 10,742 x squared plus 1, 5 plus I times x squared plus 1. Because remember, these coefficients, the a, can be complex. Here's some polynomials that are not in V, even though they're in P2. They're second-degree polynomials. So 3x squared plus 5x minus 7, well, it's got an x term, so that's not in this form. And it's not plus 1, it's minus 7. 17, well, it could be like this over here. If we had 0x squared, I could put a 0x squared plus 17 here, but it's got to be plus 1, not plus 17, so that's not in V. 9x minus 5, 27x squared plus 2. If this were a 1, it would be in V, but any number other than 1 here means it's not in V. Okay, so now we want to know, is V a vector space over C? So again, that means our field is C. Well, it turns out V doesn't contain the 0 vector in P2, so the 0 axiom is not satisfied, and V is not a vector space. Easy peasy. But what is the 0 vector in P2? It's not the number 0. Well, actually it is, but we have to prove what it is. And we prove it using the 0 axiom. We have to figure out what the 0 vector is first in any vector space before we can decide whether it's contained in any particular set, like V up here. Okay, so in Pn, the zero vector is the unique vector. The zero vector is unique. I didn't prove that, but we could do that. I think the proof is in the book, that theorem in the proof. So the zero vector is the unique vector that satisfies the zero axiom, and the zero axiom says any vector plus the zero vector equals the original vector. Here's how we would normally write it: u plus 0 equals u. But since these are polynomials, the vectors u are polynomials that we would normally write as a function, p of x, where x is the variable, like the x squared here in my polynomial. And 0, since it's really the zero polynomial, I wrote it here as 0 of x. It's a polynomial that satisfies this axiom, but I don't know what it is yet. And notice this is really important for all x in C, and x is the variable here. So for polynomials, a polynomial is really a function that's got this input x, and p of x is the output. These are the outputs we're talking about, and this equation has to hold for every possible input. Okay, so if we think about this equation then, and remember that these are numbers, well, we can use the algebra of real numbers and just think of this as an equation involving numbers. U plus 0 equals u. So what is this thing? Well, it's the number 0. So 0 of x has to be equal to the number 0 for all x in C. In other words, if we think of 0 as a function, as we did before with an input and an output, the 0 polynomial takes as an input x and outputs 0 of x, which has to be equal to the number 0. So if we put some specific numbers through there, if you input minus 5, you get out 0. If you input pi, you get 0. Root 2, 0. 27 million, you get 0. So no matter what number you put into this polynomial function, you get the output of 0. All right, so the 0 vector in Pn is this polynomial p of x equals 0 for all x in C. No matter what input you give it, it's got the output of 0. I wrote it as p of x instead of 0 of x just because that may look a little strange. This is a polynomial function p of x equal to 0, and this particular p of x is the 0 vector in Pn. Okay, so now back to the question, is this vector in V? Well, if it is, that means we need to be able to write it in the form of an arbitrary vector in V. In other words, ax squared plus 1, where a is in C, or a number times x squared plus 1. Well, we can write p of x as 0x squared, but it's missing the plus 1. So this vector is not in the form of an arbitrary polynomial in V, so it's not in V, and the zero axiom is not satisfied, and V does not form a vector space over C, and we could stop there if we wanted to. If you were going down the list, however, you would get to another axiom that's not satisfied before you got to the zero axiom, and that is additive closure. So let's look at that one really quick. Let's consider two arbitrary polynomials in V. And it may be worth taking a minute here to explain what I mean by arbitrary polynomials, because I've used that a lot. I've used that word a lot, arbitrary polynomials. If we go back up here for a minute, back to our example of some polynomials in V, these are some specific polynomials in V. So 3x squared plus 1, that is one of the infinitely many polynomials in V. It's a specific one. Here's another specific one, and what makes it specific is I've chosen a specific number here for the coefficient of the x squared. And if you compare all these, they have some things in common and some things that are different. What they have in common is they all have an x squared term and a plus 1 term. So what's common is the x squared and the plus 1. What's different, of course, is the coefficient on the x squared term. By contrast, here are some arbitrary polynomials in V, and they're pretty boring. Ax squared plus 1, bx squared plus 1, alpha x squared, gx squared, rho x squared. This is the Greek letter rho. So basically some variable, like in basic algebra, you switch from numbers to variables. So a here could be any complex number. It represents an arbitrary complex number. Same with b. Now a is a different letter than b, So we will not assume that A and B have to be the same complex number, but A could be any complex number, and B could also be any other complex number, and alpha could be some other complex number, but anything we want. And these are all arbitrary polynomials. The word arbitrary means non-specific, not a specific polynomial. Okay, so back to our two arbitrary polynomials in V, ax squared plus 1, bx squared plus 1. This is any number times x squared plus 1. This is some other any number, b times x squared plus 1. We're going to add them together and see if we get another polynomial in V. Well, if we add these two together using the definition of vector addition in P2, we get a plus b times x squared plus 2. So we get some number, a plus b, that's a single number, times x squared. So a number times x squared plus 2, not plus 1. So this polynomial is not in V. It's not in the form of an arbitrary polynomial in V. So V is not closed under vector addition, and it's not a vector space. For our last example, we'll do one that actually is a vector space, since all the ones we've done so far have not been. So in this case, V is the set of polynomials ax squared plus bx, where a and b are in C, similar to the one we just did, but instead of ax squared plus 1, it's ax squared plus bx. So a and b can be any two complex numbers, with the standard definitions of addition and multiplication in P2. And to really answer this question, we have to go through all 10 axioms and confirm that all 10 are satisfied. But for the sake of time, I won't do that. We'll just do a couple. First of all, the zero vector, which we already figured out, the zero vector in P2, p of x equals 0. Well, I could write that as 0x squared plus 0x. So that is in the form of a vector in V. And so 0 is actually in this set. So the zero axiom is satisfied. Additive closure is also satisfied if I take two arbitrary vectors in V. So again, instead of putting in some specific numbers here, I'm just going to use letters. So ax squared plus bx, I'll call that p of x. And then q of x will be two other numbers, or letters, cx squared plus dx. Add them together, I get a plus c times x squared plus b plus d times x. Well, a plus c is just a number, and b plus d is a number, so I have a number times x squared plus some other number times x, and that's in the form of a polynomial in V. So V is closed under vector addition, and the additive closure axiom is satisfied. You can check the rest as an exercise. We'll end with a theorem that I'm not going to prove. In fact, the proof isn't even here in the notes. I believe these are separate theorems in the book, and each one is proved. I actually proved this one earlier, so this was a theorem by itself, but these two are also really handy theorems. Very basic, but when we're proving other theorems about vector spaces, it's useful to use these properties, I call them, as well. So the number 0 times any vector u is equal to the 0 vector in any vector space. So V is any vector space over F. This one we already saw. This says that the additive inverse of u, the opposite of u, is equal to minus 1 times u. That might seem obvious. You might assume that's true, but you actually have to prove that this is true. And again, the proof is in the book. Okay, you survived. Like I said, this one was a little bit longer because stuff is a little harder. We're taking a quantum step here into axiomatic abstract math, so I wanted to spend a little bit more time to try to explain things more thoroughly. So we defined a vector space, we saw some examples of common vector spaces, proved a few theorems, and we did several examples deciding if given sets and definitions form a vector space, which is something that you're going to do on the quizzes and exams.